Okay, thank you. So the second part will be my academic talk. I will give some research for these 3 years of my team. I would like to introduce public information in science. It contains 4 parts. As you know, for hydrological, Okay, I think we lost some photo. But for the hydrological modeling, we know that when we construct a hydrological model, we need a lot of data. Especially it is because it is based on a watershed. It is quite large areas. So we need meteorological data, hydrological data, human activity data, underlying surface factors changes, and water quality data. A lot of data need to be collected to construct our hydrological model. And normally we are facing a problem when we are constructing our hydrological model, that is, we don't have enough data. For example, the hydrological stations recommended by the World Meteorological Organization, the control area per station should be 1,000 to 2,500 square kilometers per station. That means in China, I'm not quite sure here in Ecuador, but in China, totally we have 3,154 national basic hydrological stations. But the total national areas, we are 960,000 square kilometers in China. That means per station, it controls more than 3,000 per kilometers. That is in one big city. Even big city like Beijing, we only have less than 30 stations. Beijing is 11万 ，yeah, 11,000， 那是11000吧，11万 110,000 square kilometers in Beijing, but less than, it is something like less than 30 stations. So when we constructing the hydrological models, we know that we are facing the rainfall problems. That is a large area, but we have only one station. But as we know, the rainfall, it changes. Even for one street, we can see that here in this street, it rains a lot. But when you cross another 2 streets, it is sunny. But for one station per 3,000 square kilometers, we cannot describe this kind of situations. So we need new forms to observe the rainfall. That is public information. Here, let me introduce the history of hydraulic science development. Of course, the earliest stage when we are researching into water resources, that is direct observation stage. In the age of fishing and hunting, we just watch what we see. Then we decide what we are going to do. At the beginning, we just watch, observe. Then later on, we go to measurement phase. We need to quantify how much the water changes, how much water comes. Then we need to quantify. Then we go to the measure phase. Later on, we go to experiment phase. We go to the labs. We try to see what happens. We try to understand the hydraulical principles. Then we go to experimental stage. Later on, we go to computing stage. When the computing comes, modern times, the theoretical stage. Developing together with other disciplines, the basic concepts and theoretical systems has improved. And with the development of computer science has developed, we come into computerization stage. Also, this is the data collection development. These are the years, the era changes. First is, these are the, above is the changes of technologies. When we have papers, we try to record what is having. And later on is the 快递, what is, the transport. And then we can send the messages to other places. And when computer comes, also the data, then the mobiles, then we come to a big data era, and later on the internet, and also our mobiles can take pictures and also send pictures with videos. Then we come to the smartphone stage, that is in 1993. From here, everything has changed. Our life has changed from the smartphone coming. And before the smartphone comes, in the 19th century, we do research. First of all, we observe, then we record. Also, we send the questionnaires to other people. We collect the results. And later on, we have some sampling data. And in 1990s, we have the computers. And everything become 数字化, 叫做 digitalized, become digitalized. And in 2020, everything, including, that is after the smartphone, in 2020s, we have the ability to analyze the videos, the audience, and everything. We can get them into data. We can analyze all those different kinds of resources into scientific data. Also, the modeling concept, the diagrams is also changing. Before the smartphone, before the 这个叫做什么？ let's call it a smart area. Smart area comes. We are trying to make our hydrological models more precision. We try to collect more data. We try to have data, and the data is always the bottleneck for our modeling. But after the public information can be integrated into our research with ubiquitous sensors and public information. Later on, we will facing massive amount of data, and in the future, the modeling diagram will change to how to control the data, but we are facing the data shortage. In the future, we will change to a new modeling time that data will be too much. We are facing how to control our data. So the model framework and evolution is coming. Here let me introduce the tools. The traditional tools, as I have introduced just now, we grab samplings, we have gauging stations, also we have hydrobiological monitoring, remote sensing data, and also some radar, all kinds of these things. We call it traditional methods. That is because it needs a lot of human works. We need to collect the samples. We need to set up a national or what kind of expertized equipment to monitoring, to give us data. And also we need to always keep maintaining all those equipments. But here we have come to the new time. We have new methods. We have a hyperspectral analysis, microwave link, video image analysis, remote sensing data. All these can be used in the future to combine into our research. Here I would like to introduce a concept that is ubiquitous sensing. Ubiquitous means everywhere. That is, it first used in the social economic area rather than geographic lines. It means anywhere, anytime, by anybody, and anything could help modeling to support planning for resilience and a changing world. Here we have lots of all kinds of ways to collect the data. Everybody can collect the data, and everything can be analyzed and can be used into our future research. That is ubiquitous sensing and its using. And the tools, and here is some of the examples. The ubiquitous sensing, the concept first comes from the public science. That is some kind of projects that we are not sending questionnaires, but we ask people to be volunteers to give us data. That is some kind of projects in the US and also in the Europe, that people can volunteer, especially in the biodiversity and some kind of water resources research. That you set up a project, you ask people to be volunteer, you give some training to them so that they timely they give back some results to your projects, that you collect the public information. That is citizen monitoring. Also, people can send you text. They can give you pictures, whatever they see on the site. So this is called crowdsourcing data. This is the way, this is the crowdsourcing data. And also we have volunteer geographic information, that is something similar. All these are used in the environmental protection and disaster reduction. That is the target of how these things are being used. Something similar. And here I would like to introduce our first tools, that is smartphone. That is why we are thinking of use the public information into science. That is why we find out that the smartphones, they are very useful to collect the data, to collect not only the data, but the smartphone, they are so useful. Also, we can see that the smartphone has become the most widely used product due to their powerful function and portability. That according to 2024, the report, the global smartphone users has become 5.6 billion people. That is something 70% of worldwide populations are using smartphones. So the smartphones, they can collect a lot of data. They have these different sensors. I will introduce the sensors next. So the smartphone solves the crowdsourcing data quality issues. That is the image information. It can take photos, it has image information, and it has GPS information in the photos, in the videos, in whatever you publish to your social media, Twitter, something like that. So when you publish something, you are giving some information. Something like is your lifestyle, but when you take photos, when it rains, you says, it rains hard, I have to wait somewhere to go back home. And for that information, we don't collect what you are doing, but we collect where it rains, how hard. Later on, I will introduce some research that we analyze the rainfall from the videos. Also, GPS automatically attach time information, also the locations during the data you uploaded to whatever. This is the smartphone. It can act as a data collection tool. It also acts as an information exchange tool. Also, when it downloads some kind of apps, it turns into public hydrology platform terminals. So as a smartphone, it is very functional. As a data collection tool, it has GPS. Our mobile has GPS, has light sensors. It has gravity sensors, temperature sensors, acceleration sensors. It has a camera, it has a microphone to collect the sound. So as a mobile, it can collect so many information. It is so useful. So these are passive sensors, some are active sensors. As an information interaction media, it can publish your information into the media, into some citizens and professionals. For some, they are citizens, just that not in that topics. For example, when we are hydrologists, we don't know how the mechanic works. So in this part, they are citizens. But in the other side, you are professional scientists. Everybody can collect information and to exchange information worldwide. Now, when it comes to apps, you download some apps, you see what others give you as an information, and also you can upload your information to the apps. It comes into a platform terminals that it has more functions as big data, as open source code, as cloud computing. Something can all be done with your computer, with your mobile. This is the first tool. And also, we have cameras, we have other things. But in this, we have lots of sensors. When we have sensors, we have to thinking of the cost. That is why public information comes. Because the national or professional equipment, they cost a lot. When we are trying to set up a rain gauge station, we need expensive equipment. We need people to maintain it. And now normally they are national stations. Also we collect a lot of data. We have the internet, lots of things we need to consider. This is how the whole system should be constructed, should be thinking. And here are some of the research we have done. Firstly, is we using CCTV and also phones to measure the rainfall. This is some research we have done in our university. The code is using Python, and we use it on personal computer. We have collected various videos of raining events to determine the relationships among brightness level, classification threshold, and image filtering. Here we have collected, because this research starts in 2023, so we have collected 4 rainfalls. One is July the 3rd, July the 4th, August the 4th, August the 5th. That is 4 rainfalls in China. In Tianjin University, in our campus, we collected 4 rainfalls. That is the duration of each rainfall. And we cut the video frames, that is per second 25 images, to calculate the rainfall. So total frame size, and these are some what time we collected the data, how the brightness, how the background, everything is noted here. these are the methods how we calculate the rainfall. First is the image classification. Then we start our study to set different frames, and then we mitigate the noises and try to recognize the rainfall bars. Finally, to calculate. This is low intensity, this is high intensity. This is the time, August the 5th. This is small rainfall, heavy rainfall in our campus. This is a case study how we do it. This is background. First, at the beginning when we are trying to calculate, because the background is complicated, we can see. So first of all, we give a black background to our video. So this is without, this is with back cover. And with the back cover, that is try to analyze how with the background or without the background, the effects of our algorithm to mitigate the background noises. So we give it as this. Here we have calculated, cut it into different parts that we calculate. Here are some of the results. These are the frames. This is finally what we have collected. These are the results we get. This is the results. We have small cameras, that is mobile. The small cameras, that is mobile, and also we have big cameras, that is the monitoring camera. Yeah, some big ones. I didn't take the pictures here. Also, we have rainfall gauges because we need to verify the results. So here are the results. We can see this is the real time, and this is the accumulation of rainfall. We can see that all three cameras, they have similar results. And this is the start time and the time. And we can see that the error is different kind of error. They are all in the acceptance scope. This is another rainfall, August 5. The results. Also, rainfall was recorded. This is from the smartphone, the calculation. We can see that the red is the phone and the purple is the rain gauge. We have a rain gauge. These are the calculation. We can see it is a very small difference, and the error is less than 10%. 这是个什么东西? Oh, it seems that we lost some pictures. Also, yeah, because with the video detection, the rainfall, it doesn't rain a lot. It is not continuously rain all the time. It rains seldom. But when we are using the cameras to detect the rainfall, we need to continuing detect, we need to continuing compute whether it is rain. Or else, how can we start our algorithms? If we continuously detect, it is very resourcing cost. So we added the sound, audio part as our research. That is, when we detect the rainfall sound, then we start to calculation use the video, because the video is large and it is very resource consuming. Why? Yeah, seems that we lost some photos here. Well, these are how the algorithms, how the each part that what the steps, how we use the audios. How we use the audios, let me see. Let's just skip this part. Then we extract, first of all, we have to extract the occlusion features. That is to find out, because we have one sound, we can hear the sound as a whole, but we need to distinguish which is what kind of sounds in which period of 叫做频率 frequency. And this is where we set up our research. That is in Fuzhou campus, also in Tianjin campus. We have 2 campuses to have our experiment. This is where we set our cameras. And we have 5 locations. We did 5. In different, one location A and B is for paved walkways. Location C is a 3-line area with mixed surfaces with grass and concrete constructions and also some traffics. Location D primarily consists of a grassy area with soft ground. Location E represents open walkway with lamp posts. So this is very typical of okay. Let's see. So these are how we analyze our audios. They have different spectrum. Some are medium, some are long, some are chromogram, that we try to distinguish it. And this is how the results. Oh, okay, I see what we lost just now. That is I think here is some kind of different sound. Yeah, different sound. They are in different frequencies. Some are sex, some are insects, and some are traffics. Some are people speaking, and some when you are walking, some are from the wind or whatever. But we distinguish the rainfall sound in a special frequency. Then we can detect one start to calculate our video, to start our video calculation, to start to the rainfall calculation. This is the results. To ensure reliable, yeah, this is how the results. We can see that the results is much better than before because we have also improved our algorithms to calculate the rainfall using cameras. This is another study from another PhD student that is using the cell phone mast to calculate the rainfall and weather changes. Because when we are using smartphones, it needs signals. It sends signals to the station, and also the station will give back the signals to our smartphone. There are apps when the smartphone companies, they have the apps to detect the signal, the strength of our signals. So when we calculate the difference of the signals in sunny time and in windy or rainfall times, we can distinguish what time is what kind of weather it is. And also we can calculate the rainfall. Here we just classify the rainfall into 4 categories. One is small. Let me see. Yeah. We just calculate, classify it into 5 categories. That is no rainfall and small rainfall, small medium, medium, and heavy rainfall. So this is the calculation method. Also, we can see this is the pressure, humidity, temperature. Everything influences the signals of our smartphone. This is from another student. We use social media. That is we just collect data from social media to try to see what kind of to try to see the weather, to calculate the rainfall, to calculate the flooding, the urban flooding in the area. Because in the social media, it has time, it has location, and it has some kind of characterized pictures or objects in the photo or in the video. So that using this, we can calculate as a human, because not only human, we are tall, we are short, but also there are some kind of 参照物是什么? Yeah, some kind of references as trees, as lamp post. So also with the human height, so we can calculate what kind of flooding situation of the area. So that this is some of our research. The distribution of rainfall is roughly consistent with the map of the Meteorological Bureau. And also the generated map well describes the difference in rainfall and disaster conditions in different regions. So this is also a combination of our research altogether. And this is the urban flooding recognition, because this for the camera recognizing, that is first starts from one of our national projects, urban flooding. When we are doing urban flooding projects, we have to construct the urban flooding models. And the pipeline models, they are much more precise than hydrological models, because all the pipes, they are very in details and in very accuracies. But on the ground, everything become vague. We have one rainfall station. Even in one research area, we only have one rainfall station, and the data comes as some 1 hour per data or half hour per data. And the data we can have, we have to pay for the data, that is per 15 minutes per data, one data. So that is not enough for research. Then later on we start our research using cameras to calculate the rainfall, so that it's easier to collect the data. When we have the rainfall data, we also need to know what kind of the rainfall it gives, how much the urban flooding is. As the camera the videos, they can give us rainfall data. They also can give us the flooding data. So this is another research we do. We take some pictures. At the beginning, we take some pictures from urban flooding images using web crawlers. Because it doesn't rain a lot, it's difficult to collect so many data to do our research. So at the beginning, we use web crawlers. Then we start using many algorithms to amplify and to change our images to get more images to machine learning, using machine learning to calculate. Here because also the flooding, only when it goes to some kind of extent, the area is big enough, the water depth is big enough, it is called flooding. Sometimes it's just a small rainfall gives wet ground, it is not urban flooding. So we give it, so we use a lot of data to study. We give the low level and high level. Only one high level we calculate the flooding area and the water depths. Here is the model framework. Also using videos. Then we collect the pictures. We do the video treatment and recognize the flooding area. Then whether it is high level, if it is not high level, then we are not starting our calculation. If it is high level, then we start our calculation. To calculate, this is before, start to be wet. And this is some kind of water logging and continually increasing. Only when it starts to be wet, we are waiting. When it comes to water logging, it comes to a threshold, we start the calculation to get the area and also get the water depth. These are the references, the trees, and the lamp posts, also the traffic lights. They are at some kind of fixed height. So it is easy to use them to calculate the water depth, and also with different cameras, because one camera has limited scope of watching. So with camera combination, we can calculate the flooding areas. This is for the water depth calculation. Here is an example. In Tianjin, we have 4 streets. We set cameras to collect this data, some different streets. We set up cameras, and then we collected the rainfall videos and also the water logging videos to calculate. This is the results we can see. And the degree of water logging average accuracy is 97% accuracy. And for samples, the calculation accuracy is over 95. So these are quite good results to recognize the water logging. Some results similar. These are the different streets. These are the water depths when we have the meters to detect. And this is the modeling. So we can see with the real measurement and with the modeling, the results can 叫做一致 consistency. And with all this data we have collected, we have analyzed, we also have our own flooding model. This is urban flooding model we written in Tianjin University. Some new techniques, that is our something similar. The principle is similar to swim. I don't know whether you are using water logging urban flooding models or not. They are mainly pipeline models. Underground. At the beginning, we need to draw the pipes and the nodes handling. With our hands, every pipe, every node, we draw it. We give the parameters of each pipe, each node, whatever. So our models have solved these human activities to be automatically. One is G-based. We have made all the pipelines underground can be seen in our map, so we know which node is where. The second is multi-scale, is that we can calculate. We can select a specific area to do a new modeling. So once we have constructed a model, we don't need to construct it again and again. in different details. We can just cut a piece, then we change this piece of models to save it as a new model and to calculate. After calculation, everything is okay. We can put it back to the big model, to the urban scope to be simulated. Yeah, combine. This is two-dimensional. That water can be seen when it goes up to the ground. We can also model it, and the performance a little faster than swim. So this is an example. The different bars, how our model looks like. Yeah, these are the. So it is something similar to GIS. When you're using GIS, you can see our model is based on the GIS surface. So all the using habit is similar to GIS. So it's quite easy. And also we can change all the parameters. And we can give the land use map and all kinds of maps automatically into our models so that we don't need to draw the pipes, we don't need to draw the nodes, everything can be worked automatically. Then later on we can modify or change whatever it is not so correct handling. And data can be automatically processed. This is our model. This is some of the results. It can give the status report, time sequence, form, and simulation results, and we can see what kind of the situations our model is. And this is surface flow modeling. This is the rainfall intensity, two-dimensional modeling. These are an example in Suqian City. We cut it into 3 pieces. This is because these 3 pieces, there are rivers between these 3 areas, so they are independently, in fact. But this is how we set up our model. Nearly 2,800,000 in wells and some similar pipes. This is a very complicated model. This is where the model is and where the flooding area is. This is the results. Rainfall and the urban flooding in some different areas. These are 2 rainfall. What? 怎么回去了? Where is it? 好的嘛，去哪了？这家伙也太多了吧？是吧？在这儿差不多。Okay, like this. 是这儿吧？不是？哦 ，OK。Yeah, okay. These are the results indicate that the trend of different models, the trend of, yeah. What's this? Oh, this is too fast, okay. They're not the results. Yeah, this is some first results, the same, oh, this is also not. Here is the results that shows the water logging is something similar to the rainfall, but a little bit time delayed. That is consistent with the nature principles of how the rainfall and how the urban logging, what happens, because there is a time delay. And it is consistent with the rainfall and the urban logging. That is shows that the model is reliable to be used for future modeling. Also, we did some researches into what is it? Urban flooding areas. Okay, and here, because as we can see, this is a very complicated model. It has some 30,000 pipes and nodes. Normally, it costs some more than 20 minutes to calculate this complicated model. And with the model, as it is more complicated, it costs time. It requires a better computer, and also there will be a lot of errors happens with the complicated model. So we also try to consider, because we are working on public information with lots of information, does it necessary to use so many data to monitoring one same area, the same model? So here we made a simplification of our model. That is, the full model is, we cut one piece of the model. The full model is 5,000 nodes. And the first simplified is, we see here, it's the same time duration, the same rainfall, modeling steps is the same, simulation time, it changes. The first simplification is that we removed all pipes which are less than 10 meters. The small pipes, we remove it, less than 10 meters in length, and diameters less than 100 millimeters, but maintains connective of pipeline network. And then we gave a second simplification, that is, remove all pipes which are less than 10 meters in length, and according to the simplification first. Also, we removed all the pipelines slopes less than 0.3 and maintains connective of pipeline network. Then we gave the modeling, the simplification 1 scheme, that it gives less than 2,000. Beginning is 5,000. After the simplification first, simplification 1, it is less than 2,000. Later on, it has even decreased to 800 nodes. And then we can see the modeling time. It also changes. For the full model, it costs 200 seconds. That is some 4 minutes. The first simplification, the calculation, it only costs 17 seconds. And the simplification 2, it only costs 11 seconds. So we can see even the 5,000 nodes simplified to 2,000. And the calculation time, it decreased dramatically to 17, to less than 10% of the total calculation. So here we are trying to understand how the simplification of the model, what it will happen in our modeling. This is compare the water level, the different, what is it? Simplification, for here, that is different. We have calculated 3 different schemes of 1 year return period, 5-year return period, and 10-year return period of rainfall to see the simplification of each models, how it performed. Then we can see that such a location is similar, the location percentage. The full model is 53, the simplification 1 is 54. So the results are very similar. But for when we simplify it too much, we can see that the results will change. Because the small pipes are all removed, so the water logging problems, it doesn't happen. Because normally when it rains heavily, the small pipes, it confines how the water underground it goes. But without the small pipes, it has to be flooded into the ground surface. So this is some result of our research. And the last part is the future. So here in the future we are facing the big data era the time, and so that in the future we will have lots of data with cheap sensors, such as the video, the cameras. Normally it only costs some less than $100 US, maybe some 50, 40, only the cost. It's very cheap and it doesn't need to maintain. And nowadays we are having cloud storage that all the data can be uploaded to the cloud. So in the future we are going to enter a new era, a new time of lots of data. Because in China, I'm not sure here in Equator, in China the cameras are very, very dense, some 50 meters per camera.